Hi everyone. So we have already seen the first part of this advanced customizations. Now let's move ahead with the second part. I'll just open this code and the same place where part 1 was uploaded, you can find the link for the part 2 also. I'll open it. Let's see in the collab what we have done in the code and how it's working. So first let's go with the summary. Okay, so this is again advanced Keras and PyTorch constructions. So we have used TensorFlow and PyTorch. We have used the same fashion MI and IST dataset. The training and validation split is 5000 and 1000, and the base model for all is 3 layer MLP, that is 784, 128 and 64, and the base layer is same for all, and the optimizers we have used is Adam, and batch size is 32, and loss is sparse categorical cross entropy. So this setup we have done, and once the setup is done, we'll do multiple sections. The first section is custom learning rate scheduler, one cycle that we will do with TensorFlow and PyTorch, and we will compare the results. And then next thing comes is the custom dropout, and then custom normalization, and after the custom normalization we have tensor board, and after tensor board we have custom loss functions with Hoover loss, done with both TensorFlow and PyTorch. And then we have custom activation, initializers, regularizer, and constraints with both PyTorch and tensors. Once that is done, we have custom metric using Hoover metric. We have defined custom layers using PyTorch and tensor. And once that is done, we have custom models, residual block and residual model. And after that we have custom optimizers and momentum, and then we have custom training loop. And the last section is weights and biases that I have covered in a separate notebook that we'll see after this. So let's see code by code with the first cell. I'll move to the top, just connecting it. Okay, so in the first cell, we are just installing the libraries, dependencies, TensorFlow, Torch, NumPy, everything that is required, all the things we are installing. Once the installation is done, in the first cell, we are loading our data set and we are dividing it. We are keeping only 5000 samples to keep the training fast. So, see, we have train data is 5000, and the test data is the train data is validation data is the 1000 in the size from 5000 to 6000. So we'll print the shape so we can see it's 5000 for training, validation we have 1000, and test we have 10,000. So this is the data split that we have kept. Now next is the first part, that is the custom rate learning scheduler using TensorFlows. So we have one cycle scheduler in which we have defined maximum LR steps. Step by default step is 0 and LRS, and we have then one more function on batch begin that has set half is equals to step by 2, and then we are using the formulas. We are using dot assign instead of Kira's backend set values, and we have used Kira's dot input as the first layer instead of shape. So this is Kira's dot input as the first layer, and then we have defined three different layers. And then we are compiling the model using Adam optimizer, loss as sparse categorical cross entropy loss, and matrix as accuracy. We are passing the number of epochs and steps, and then we are calling our one cycle scheduler with maximum LR and steps is equals to n steps. and then we are doing the model fit, and we are storing the history, and we are plotting the figure on basis of it. And we can see its final accuracy comes to 8.40. And if we see custom learning rate scheduler, so PyTorch, this we have seen with the help of TensorFlow. Now we will see using the help of custom learning rate scheduler. So PyTorch has a Torch Optim LR scheduler. We subclass lambda LR to replicate the same logic cycle. So what we will do, first step is we will define simple PyTorch model, that is this simple. In the second step we will set up optimizer and one cycle scheduler. And once the setup is done, this is the model setup. And once that is done, the lambda LR multiplies the base LR. So lambda LR multiplies the base LR by the return lambda value for the each step. So for each step it will multiply the base LR with the return lambda value. So that's what one cycle lambda here does. And then we will convert the data into tensors, and we will pass them through the training loop. In the training loop itself, if you see scheduler plot step, so it will update LR for every batch, and then we will plot the output, and we'll see, we can see total LR step record is at 784. So that's how we do it using the PyTorch. And the next thing comes is custom dropout, MC alpha dropout for TensorFlow. So what is MC alpha dropout? What MC alpha dropout keeps dropout on during interface 2, inference 2. So running inference n times gives uncertainty estimates. Each gives slightly different predictions, and alpha dropout preserves the mean and variance of the input better than the regular dropout, and that's why it's better. So in regular dropout, we do not preserve the mean and variance of inputs, but here we alpha dropout preserves it, and which results in better uh, outputs than the regular dropout. So first step is we will define, here we are doing with TensorFlow. So first step is we will define MC alpha dropout layer, and this is designed for SELU activations, and we override the call, so dropout stays on during the inference. So here we are overriding it, and then we will build a model using SELU MC alpha dropouts. So SCLU and alpha is recommended combo for self-normalizing networks. So here we are building that model. Once the model is built, we will compile the model, and then we will do model fit. And in inference, MC inference, we will run 100 forward passes, and each pass gives different predictions. So dropout being gone. So average prediction across all the hundreds we will run here, and then we will show the uncertainty for the first sample, and then we will plot the graph accordingly. So we can see predicted classes are 4 and the true labels are 4, and we can see the probability is highest on the 4. The uncertainty is standard, we can see the uncertainty also here. So this is MC dropout mean predicted probability sample, we can see where 4 has the highest probability. Now the same thing we will try with PyTorch. The idea is same, keep dropout out during the inference and use model.train, and PyTorch makes it easier, just never call model.eval. So define the model with standard dropout. Here we will define it. It will stay on for always, and then we will train the model. Once that is done, for each epoch we will do the training, and then in step 3 we will do MC inference, 100 stochastic forward passes. We do not call model.eval, so that dropout stays on for all the cycles. And then we will run average over 100 runs, and we will keep storing the uncertainty. And then we will print out the results, the predicted class and everything. So again we can see the training is done, predicted class is 4 with the highest probability, and uncertainty also we can see here. So this is how we use PyTorch for custom MC dropouts. Now, custom normalization, max norm dense. So, max norm constrain each neuron's weight vector for norm is less than equals to max norm. So, it prevents the weights from growing too large. It stabilizes the training, and it is useful when we don't want to use batch norm. So, we use custom normalizations. So, first we define the max norm dense custom layer. So we'll define this layer, and then we will define standard weight plus biases like just a normal dense layer we will do here. And then we will define a call function to clip the weight, so each column's L2 norm is less than equals to max norm. Then we will define a get config that is needed to save or load the model correctly. Then we will do step 2, that is build model using max norm dense. And once the model building is done, we will do model.compile, and then we will train the model with model.fit, and we will check the weight of the norms, and we will print the output to see. So we can see max weight norm is 1.61, and value validation accuracy is 8.6. Now let's see how we can do custom normalization and with max norm with PyTorch. So PyTorch has no built-in constraint APIs like Keras, so we apply max norm normally after each optimizer step. So what we will do, we will define a model, we will define a max norm net model. In that we'll define forward pass, and then we will apply max norm, we'll define a apply max norm function, and after each optimizer step we will clip the weight to the max norm. So only clip if norm exists to norm. So here we are clipping it, and once that is done, the second step is training with max norm applied after each step. And we are for each spoke we are doing this, and here we are enforcing the constraint. Once that is done, we will verify the norms are created, and then we will do model dot evaluation to do the quick accuracy check, to check the well accuracy, and we can see the accuracy comes 0.786, and max weight norm comes 1.0, which ideally should be less than or equals to 1, and it is exactly 1, so we are good. Now the next thing comes is the tensor board. So how do we implement tensor board using TensorFlow? So TensorFlow visualizes laws, curves, weights, gradients live, much better than printing laws and seeing the trends visually. So what we will do, we will create a log directory, and we'll define a tensor board callback where we will define the weights and everything, and then we will build a train model for TensorBoard callback, and then we will compile and train it model.fit, and then we will launch the TensorBoard. So once we will launch it, we can see the live data and the details. So this is how we can see the live graphs, distributions, histograms, time series, everything we can see live in this TensorBoard. So this is how we implement TensorBoard using TensorFlow. Now we will see how we implement using PyTorch. So PyTorch uses torch.utils.tensorboard comma summary writer to log, and we manually log the loss plus accuracy for each epoch. So first we will import this torch utils tensorboard with, and we will import this summary writer. In the first step we will write the pointing log directory, and then we will define the model, optimizer, and the loss function. Once that is done, we will train and log the metrics for each epoch. We are here running for each epoch, and once that is done, in the same flow we will log the train loss using write.add scalar, and log the value accuracy again with write.add scalar. And once that is done, we will close the writer. We should always close it once we are done writing, and then we will log the TensorBoard to see the accuracy flows and chart live. So you can see this, we can see the live accuracy graph, and similarly we can see the loss graph also. It is also live, so we can do it using like this, using the PyTorch. So after the tensor board, the next thing comes with the custom loss function or the Hubble loss using the TensorFlow. So what is Hubble loss? Hubble loss equals to mean squared error for small errors and MAE for large errors. When there are small errors, MAC is the Hubble loss, and when there are large errors, MAE is the Hubble loss. The less sensitive to this Hubble loss function is less sensitive to outliers than pure MSC and great for regression tasks. Uh, let's see now how we use it. So first we have defined a Hubble loss as a class. So we have defined a class here. Um, Here we have defined delta as a threshold between the MSC and MAE regions. And then we have defined a call function where we are defining MSC zone if it's small errors and MAE zone for the large errors. And then we are returning it, and this get config is to get the configurations, and then we are making the target here. So we are giving the train and value mean. Once that is done, we will build a regression model here. We'll do model.compile, and then we will train the model using model.fit. And once that is done, we will plot the loss curve. If you see, we have this training loss and this is the validation loss. And final well MAE is 0.10. Now we will implement the same thing using the PyTorch. So we subclass the NN dot module to define our own loss functions, the same delta logic as cell 10. So we'll define a Hubble loss class with this function, and then we will define a forward function. Prepare regression data, we will prepare this regression data here, and then we will build a regression model. Once the model is built, we will define the optimizer and the loss functions, and then we will do the training part. Once in the training also we will call this Hubble loss function, and then we will plot it. So if you see, we have plotted it, and it's a stiff Hubble loss, train Hubble loss. We can see it is decreasing with number of epochs. So the next thing is custom activations, initializers and regularizers constraint. We define all four in one cell and plug them into one model. This shows how modular Keras really is. The first step is custom activations, that is leaky ReLU. Standard ReLUs kills the neurons, and leaky ReLUs allows a small negative values, that is no dead neuron. So here we are defining our leaky ReLU, and then the second we have is the custom glorot initializer. That it is why we use it, because good weights in it prevents vanishing and exploding gradients. Blood glorot scales weights by input and output size automatically, so that's why we use it. The third step is custom L1 regularizers, and it pushes the small weights to zero, then sparse model and less leads to less overfitting. That's why we use it. And the fourth step is custom weight constant, that is positive weights, forces all the weights to stay positive. That is useful in specific architecture like NMF style networks. Now the next step is we'll build model using all four custom components. We have given all four custom components here, and in the dense layer we have defined all the four components, and we will do model.compile, model.fit, and then we will verify all weights are positive, and minimum weight should be greater than or equals to 0, and we can see it's 0, and validation accuracy is 0.761. The next thing is custom activation, initializer, regularizer and constraint PyTorch. Sorry. So the first step is again custom activation, that is leaky ReLU with NN dot module. Then next is custom glorot initializers as a function, then custom L1 regularizer as a penalty function, and custom positive weight constraint. And then we will again build a model and apply those custom components. And once that is done, we will train with L1 drag and positive weight constraint, and we will verify the output. And we can see the output comes as 0 0.0, which is correct. It should be greater than or equal to 0, and the accuracy is also good. Moving toward next is custom metrics, Huber metric TensorFlow. So a custom metric tracks a value across the batches correctly. Built-in matrices may not match your loss. The custom metric lets you track exactly what you care about. The key difference from loss and metrics accumulate across the batches, and losses are computed per batch. So this is the main difference. So first step is we will define Huber metric. So we have defined this class, we have this init function. It adds weight to create variables that accumulate across the batch, and we have this Huber loss functions that will store the error. Is it small, then small, and if it's large it will be MAE. Then we have this update state called every batch accumulates total loss and count. Then we have this result called at the end of epochs return mean Hubble loss. We have reset state called at the start of each epoch to reset the accumulators. We have this get configuration to get the configurations. Then we have this build regression model with Huber metric. So we will build a model using Huber metric and with the defined layers, and then we will do compile the model, and we will train it, and then we will plot the metric curve. So we can see this is the custom Huber metric per epoch curve, and it's working perfectly fine. The next thing is custom metric Hoover metric with PyTorch. So PyTorch has no inbuilt metric APIs like Keras. We build a simple stateful metric like class manually. So we define first a stateful Hoover metric class, which accumulate the total loss across the base, accumulates the sample counts. Then we have this update function called for every batch. We have this result function called at the end, reset called at the start, again same everything. Then we will build a train model. We'll build and train the model for tracking Hoover metric. So here we are building the model, we are training it for the epoch, and then we are printing the plot to see the values. So you can see initially it was something, but later it came down to 0. So it's good. Next is the custom layers. So we build 4 custom layers and stack them into model one by one. So first layer we will make exponential layer, second layer is my dense layer, that is a dense layer built from scratch. Third is the add Gaussian noise, it will add noise during the training, and my layer norm normalizes its samples activation. So layer 1 is the exponential, we are defining here it. The second layer we are defining here as my dense layer, and the third layer we are defining is add Gaussian layer, and the fourth layer we are defining here as the layer norm. Once that is done, we will build the model, we'll train the model, and we'll print the summary. So if we print the model dot summary, we can see these are the layers, these are the output, and these are the parameters. So we have built a model successfully with the custom layers. Now the same thing we will do with the PyTorch. We will build a model with custom layers with PyTorch. So let's see. We will first again define exponential activity. We will define the myDense function, the Gaussian class, the my layer norm class, and then we will stack all the layers into one model. We can see we are stacking all of them here, myDense, add Gaussian, all this into a one model, and then we are training the model, and then we are printing it. So we can see the layers, it's my dense, then add Gaussian, then this, so all the layers are added here. Once that is done, we'll move to the next part of building custom model with residual block and residual model. So residual connections add the input directly to the output of a block, and it skips a connection. It solves the vanishing gradients in deep network, the problem of vanishing gradients. So let's see how it does. So first we define a residual block, 2 dense layer inside the block, and then we will define the call function. It skips the connection and add the inputs directly to the output, and we will define full residual model also. It will include all, it will stack the 3 residual blocks inside the residual model, And once that is done, we will define a call function that will project input to 128 dimension first, and then we will build, compile and train the model, and we'll print the summary. So once we print the summary, model is residual model. We can see three residual blocks here stacked in the model, and these are the parameters. Next is the residual block in model using the PyTorch. So first we will define a residual block here. Once that is done, we will define a full residual model using the residual blocks. Here we are using three residual blocks in the residual model, and then we will train the model and evaluate it, and visualize the block structure. So if you see, we have run it. The model structure looks like residual model. Inside we have block 1 of residual block, block 2 of residual block, and block 3 of residual block. So this is how our model looks. Now the next is a custom optimizer, momentum with TensorFlow. So momentum optimizer accumulates a velocity vector in a direction of persistent gradient. It faster convergence than plain SGD and less oscillation. The formula is given is V is equals to momentum into V minus LR into grad. That is W is equals to W plus V. So first we'll define the custom momentum optimizer here, and then we will define the build function. It's called once to create velocity variable for each weight. One velocity variable per trainable weights we define here, and then we define this update step. It is called for every step for each weight and gets the weight's velocity variable. Update velocity will define here, and then we will update the weight, and then we have this get configurations. After this we will build the model, will compile with custom optimizers, and then we will train it. So in the custom optimizers, see, we have given optimizer is equals to my moment optimizer. So we are compiling it using the custom optimizer, and we are training it, and we are comparing with plain SGD, and we'll see how it works. So you can see the blue line is the custom momentum, and the yellow one is plain SGD, and the value accuracy is much higher for the momentum, that is the custom one, and SGD is less than the custom one. So now we will implement the custom optimizer using PyTorch. In PyTorch we subclass torch optimizer. We manually implement the velocity and update the logic. So step 1 is define custom momentum optimizers. Once that is done, we will build the model, and here we are defining the optimizers in the model while building it. This is our custom optimizer, and then we will train it and plot it, and we can see it's plotted here. The next thing is custom training loop. So in the custom training loop, we will instead of model.fill, if it we manually control every step, full control over the forward pass gradient, and we have Kira's sequential. We will build the model here. We have defined optimizers, we have defined metrics to track, and then we are defining one training step using, we are defining one validation step, build on TF data pipeline, full training loop, and once that is done, we will collect the results and we will plot it. So this is a custom training loop accuracy plotted. Once that is done, we will try the same custom training loop with PyTorch. PyTorch always uses manual training loop. This is standard PyTorch way. We add extra features, gradient clipping, LR scheduling, and best model saving. So we'll build the model, we'll add the schedulers here, and then we'll prepare the validation tensors, and we will do a full custom training loop here. Once that is done, it will include validation phase, LR schedule step, everything. Once that is done, we'll restore the best weights, and then we will plot it. So this is how we use it in the PyTorch, the custom training loops, and that's all for this file. Let me just quickly go through the last part of this. One is the weights and biases. So let's go through it also quickly. I'll just close this and I'll open the weights and biases file. This is the last part of the second part of this assignment. Let me open it. Okay. So what we are doing, we are using W and B for weights and biases. We are importing here. I have passed my weights and biases key, and I am logging into WA and B site. Once I have logged in, it says currently logged in as Prachi Gupta, and then I'll load my data set. Once the data set is loaded, I'll initialize W and B. I'll build a model and I'll compile it and I'll train the model, and I'll log on to W and B and I'll plot all these details. I'll log my epochs, my training loss, my training accuracy, everything, and I can see a live board of it on the WNB website. Here the link is given. I can click it and I can go to that page. So that's how I use WNB. And to initialize the new run, I can again do init. I can give a data, I can give the model, I'll train it, and I'll just do finish, and it will again relaunch it with the updated data. And this is how WNB site works. And that's all for the second part. So we are done with all the collabs, and that's all for this. Thank you so much.